Good morning and welcome to this lecture. So, in today's lecture, we will be talking about the prefix coding. So, initially, we will have some recap regarding the previous lecture, such as source encoding theorem. This we have already seen. So, if we want to represent any information more efficiently, then we need to have the source encoding scheme. We will employ some coding scheme at the source and we try to represent the information in a better way. That is the idea of source encoding. And to do it more efficiently, we need to know the statistics of the source. Especially, we are talking about the probability. We should know the probability of the source. I mean, the symbols emitted by the source. So if we know that, we can represent every symbol emitted by the source in a better way. So we have already seen some of the variable length coding schemes. In that case, instead of representing every symbol emitted by the source with the equal number of bits, we have employed different number of bits for every code word. I mean every symbol as a code word. For example, if there are two symbols emitted by the source, uh, we may represent it by equal number of bits, or we may represent the code words by different symbols by different number of bits. For example, we will consider there are four symbols generated: A, B, C, and D. Can we represent all these four symbols by equal number of bits? Of course, it is possible. For example, A is represented as 00, B as 01, C as 10, and D as 11. That's a very easy way of representing the symbols in terms of codes. Instead, we may do it in a different way. For example, A is represented by just one bit, B is represented by two bits, and so on. In a different way, maybe C represented by three bits and D again represented by one bit, and so on. So that is called as variable length coding. I think we have seen some of the variable length coding schemes. So in case of variable length coding, the main idea is not every bit is represented by the same number of bits. The symbols are not represented by same number of bits. So we have also seen the average length of the code word. So when there are k number of symbols, and if LK represents the length of any code word that is used to represent a symbol k, then the average code word length is nothing but pk and lk. So pk is the probability of any uh, code word or the symbol, and lk is the length of the code word that represent a particular symbol k. So this is computed for all the k symbols. So that gives the average length of the code word. So this equation we have seen earlier. So this is nothing but the weighted length, because we have the probability here, probability of occurrence of a particular symbol k, and if that particular symbol is represented in terms of code words, then how many bits we have in that code word, that is lk, right? For example, a is represented by just one bit, b may be represented by two bits, then lk becomes 2, so on. Okay, then we have also seen the terms such as coding efficiency. The coding efficiency, eta, is nothing but L minimum divided by the average code word length. So L minimum indicates the minimum length of the average code word length. And there is a condition that the average code word length can be at least or value of the entropy. So H represents here the entropy, and L prime represents the average code word length. So the average code word length can be as small as the entropy. So it says greater than or equal to, not less than the entropy. So it can go up to the value of entropy, but not less than that. So this gives the lower bound of the average code word length. So based on this, we can redefine the efficiency. So this is a general equation for efficiency we have seen in the earlier lectures. The efficiency is given by the entropy divided by the average code word length. So when based on this condition, when L prime reaches its minimum value, then the efficiency you can compute. So this becomes equal to this, right? Because L prime can be greater than entropy or it can be equal to entropy. So when it becomes equal, we have the highest efficiency. Okay, now we will see today's regarding today's lecture, that is prefix coding or encoding. So initially we will see some of the background why we need to have a prefix free encoding. So in case of English language, there are different characters and we can represent these characters, for example, A, B, C, D, using ASCII, and each character or each symbol will occupy 8 bits. So that is the idea of fixed length encoding. For example, A, B, C, D, whatever. We represent every symbol by 8 bits. That's in ASCII. So this is a fixed length encoding. So if there are n number of characters, we need 8n bits to represent these symbols in ASCII. But our target is to reduce the storage space, or if you want to transmit them, we need to consume minimum bandwidth because we always have the constraint. So what we do is we will use some source encoding schemes. For example, we may zip those files, compressed files. There are different zipping schemes to compress the size of the file during transmission or storage, and then we unzip it at the receiver where we can get back the original data. So we will see some better ways of doing this. So in real life, we know that in if you consider English language, these characters of English language, they do not appear with the same frequency. For example, different letters will have different probability of occurrence. Okay, so some characters are very common and some characters they do not appear so frequently. In that case, given a message or a stream of symbols, if we can understand which symbol will appear more times or very frequent, or which symbol is not so frequent, in that case the frequent characters are encoded with a few bits and infrequent characters are encoded with the more number of bits. So this is the idea we have seen in the earlier lectures. So by that we can reduce the storage space. So basically we are achieving a trade-off here. We are having more bits and saving more storage space and assigning more frequent characters with fewer number of bits, because when bits are less frequent, if we can assign them with more number of bits. When the bits are more frequent, they appear many number of times in that particular data stream or a message. In that case, if we assign fewer bits, then we will be consuming less space. So this is these two lines is basically the idea of trade-off. We are achieving a positive thing, that is reducing the storage space, and also we will be representing it more efficiently. So this is basically the variable length encoding, because we consider the frequency of occurrence of every symbol and assign different number of bits. So we will see an example here. In case, so this example says how we can uh, achieve efficiency by employing variable length coding instead of a fixed length encoding scheme. Suppose we have here maybe 100 characters, and they occur with the characters are A, B, C, D, E. And here A occurs 45 times, and the remaining symbols B, C, D, and E, they occur 11 times each. So out of 100 characters, A appears 45 times, and remaining 55 times, these four characters will appear each with 11 times. So now, if we use the fixed length encoding, where each character, that is A, B, C, D, and E, are represented with the 3 bits, then how many bits in total do we need? For example, to represent A, we need 135 bits, right? Because A appears 45 times and we are representing A by 3 bits. Similarly, the remaining characters B, C, D, E, they occupies 165 because remaining 55 times out of 100, the other characters will appear B, C, D, and E. And each one is represented by 3 bits. So 55 multiplied 3. So altogether we need 300 bits. In case if we use the variable length coding, for instance, A is represented as 0, B is represented as 100, C is represented as 101, and D is represented as 110, and E is represented as 111, then how many bits do we need? A is represented by just 1 bit and it appears 45 times. And remaining 55 times the other characters will appear, and each one, that is B, C, D, and E, are represented with 3 bits. So altogether we just need 210 bits. So this is a variable length encoding where we assign different number of bits for every symbol. This is a fixed length encoding where we thought let us assign equal number of bits for every character. So the fixed length encoding requires 300 bits, variable length encoding requires just 210 bits. So we have a better saving here of about 30%. Instead of 300, we are just having 210 bits. So let us think more about this. Do we have any better scheme? For example, A is represented as 0, B is represented as 1, C is represented as 00, D is 01, and E is 010. So is it a better scheme to represent? Because when we represent any of these symbols as different code words in binary, our main objective is to either store them or to transmit them. So when you store it or transmit it, the other side, that is when you decode, you should be able to represent every symbol uniquely. I mean, it should be readable or decodable at the receiver. Of course, every symbol here is represented uniquely, right? Because every code word is different. But can we actually decode them properly? We will see that. So here, this scheme requires less storage because we don't represent every symbol by equal number of bits, because each character is encoded with fewer bits, right? For example, A and B has just 1 bit and only E has 3 bits and so on. So of course it requires less storage than using same number of bits for every code word, I mean every symbol. But what is wrong with this encoding scheme? Is it totally a better scheme? We will see that. For example, A is 0, B is 1, C is 00, D is 01, and E is 010. Of course, this is a variable length coding, but is it totally okay to decode? Okay, we will see this here. Suppose we want to decode 0101 at the receiver. Then what would be your guess about these symbols? Suppose if you receive this bit pattern or the encoded data at the receiver, then how will you understand what was the what was the symbol that was transmitted? For example, when you see 0, do you consider it as A? Next you see 1, you consider it as B. Next you see 0, okay, maybe again A. Next you see 1, that is means B, so it is A, B, A, B. Is it right? Okay. Is there any other way? A is 0 is A, 1 is B. Next, we have 0, 1 together. That represents something? Yes, it represents D here, 0, 1. So is it A, B, D? Or 0 is A? Next, 1, 0, 1. No, we do not have any. Or maybe we have 0, 1, 0 here, 0, 1, 0. So here, when you see 0, 1, 0 first, you consider it as E, and there is a remaining 1 here. Is that B? So is it like EB? So yeah, we have different options here, right? Is it ABD, A, B, and 0, 1 represents D? So is it ABD or ABAB or D and D? That is 0, 1, 0, 1, D and D, or EB, and so on. So we are totally confused if we receive this kind of encoded sequence at the receiver, then how to decode this? Then we have a confusion here, because this code can represent different symbols. The main reason what we call it as here is one code word is a prefix of another. Is it so? For example, here 0, 1, if you see, is a prefix here, 0, right? Or if you see each bit here 0, 1, then if you see this one, you have a prefix here. So in this case, every symbol is represented by different or unique code word. That's right. But there still exists some confusion during decoding, because some of the bits here are the prefix of another one, right? 0, 0, 0, you have a prefix here. So this gives the main difficulty at the receiver. The receiver may not decode the bit patterns in a unique way, even though when we transmitted them uniquely, but at the receiver there is still exists a confusion. For example, this bit sequence, what's the meaning of this bit sequence? Is it ABD or ABAB? What, EB? We don't know, right? Because there's a confusion due to these prefixes. So to avoid the problem, we generally want that each code word is not a prefix of the other. For example, in the previous case, we had 0 and 1 for A and B. That were the prefixes of some other codes, D or C. So that should not happen. So such an encoding scheme is called as a prefix code or prefix-free code. So when we avoid this condition, we will get an efficient prefix code, or it also called as prefix-free code. And generally, we can represent a prefix code by a tree diagram. Or if we have a tree diagram, we should be able to represent it as a code. So we will see that in this slide. So how to represent the code word as a tree. Okay, so now when we write a tree will have a root. From the root, we will have the branches, one moving to the left, other moving to the right. So each edge or the branch is labeled by a bit. The bit may be either 0 or 1. And then each leaf is represented by a symbol. That means when you have a edge will end with the leaf. The leaf is nothing but a symbol, maybe A, B, C, D, and so on. And then the labels on the root to the leaf path is nothing but the code word of that particular symbol. We will see with an example how to use these 3 steps. So we have the example here. That means we are considering the different symbols here, A, B, C, D, E, and they are assigned with the different code words already. I will see how to construct a tree for such a scenario here. But an important point here is a prefix code has the important property that it is always uniquely decodable. So this is what we have seen in the previous slide. In the previous slide, it was not uniquely decodable, right? Because we had a confusion. Some of the code words were prefix of some other code words. So that should not be the case. So if it is not the case, then a good prefix code will have the property that every symbol is uniquely decodable. We will see whether this one is a good prefix code or not. Okay, we will use these 3 steps for this particular example and construct a tree. So the first step here, we have shown all the steps here. For example, this is the root of the tree. From the root of the tree, we are going to write the branches or edges. So one of the edges will be named as 0 and another edge will be named as 1 or labeled as 1. And then the edge will end with a leaf here. So what do we have? A represents 0. So here from the root you move here. Here we have a 0, so that represents A. We already got A. And then we have another edge here, right? One is on the left side we have 0, on the right side we have 1. This is how we write the tree. So on the right side we have 1. So 1, after that we have a leaf here. That's the intermediate. And from this point or this leaf we have again one branch going to the left, other going to the right. So the left side we label it as 0 and the right side we'll write it as 1. And again we'll continue this. So here we have one more leaf, intermediate, and then from the left we will label it as 0, on the right we will label it as 1. And finally we arrived at B. Is it so? Because B is nothing but 1, 0, 0. We know what is B. How to write B in this tree? So we have to do this. We from the root on the right hand side we write a 1 here and arrive at an intermediate leaf. And again this leaf will have two branches 0 and 1. But we need to travel along 1, 0, 0. So initially we traveled at 1 and then we travel to 0, and from this point again we have a 0 and 1. So we will travel to again 0. So we will be tracing 1, 0 and 0 that leads us to the symbol B. Similarly, we have another symbol here, 1, 0, 1. So from the same path, 1, 0, 1 that leads us to C. Okay, so this part of the tree is complete. And we have still few more bits, symbols remaining to encode. So right now we are left with D and E. So already we have traveled from the root to this point with 1, and now we have to build the remaining part of the tree. So the right hand side we have marked it as 1 already, and we have arrived at some intermediate point here. From this point we have again two possibilities, either 0 or 1, because we are using a binary encoding scheme. So on the left hand side we always mark it by 0, on the right hand side we mark it by 1. So if you see the entire tree, always we follow a uniform pattern. Left hand side is marked with the zeros and right hand side from any intermediate node is marked with 1. Okay, so then what do we get here? It's E, right? Because 1, 1 and 1 is E. So 1 on the right hand side, again right hand side 1, again right hand side 1 is E. Similarly, D, how to get D? It is 1, 1 and 0. See, always we trace a symbol from the root 1, 1 and 0 that leads us to D. So this is the way of writing the or representing the encoded bits in the form of a tree. So we must be very careful regarding this, that on the left hand side we use zeros. Anywhere if you see on the left hand side we have zeros, and we extend on the right hand side we have ones, and we extend the tree until we reach our symbol. For example, if there was one more level, maybe 1 1 1 and one more 1, then we need to extend this. Here 1 0, here 1 1. So this is actually the required symbol here. 1 1 1 and 1, maybe that is F. Okay, so this is how to map between the symbol bit pattern and the tree, and we have followed all the 3 steps here. So finally, in the final step, when you travel the path from the root to the leaf, you get the code word. For example, for A, you travel from the root to the leaf. Here you get its code word 0. Okay, now we have a homework here. You must try this homework. So is it a prefix code? You need to find out. So I have given here a bit pattern. So you need to write the tree diagram for this, and you will come to know whether it is a prefix code, proper prefix code or not. Similarly, we have one more example here. So for this also you try to write the tree diagram and find out whether it's a prefix code or not. So how to decide whether it's a prefix code or not? If every uh, symbol is decodable, then it's a prefix code. In the previous example, yes, it was a prefix code. But we have seen some earlier examples where we had a confusion regarding decoding. Do you remember that in the earlier slides? So that is not a prefix code because we cannot represent every symbol in a unique decodable way. Then it is not a prefix code. So you see, try to write this as a tree. If you can write it properly, then of course it is a prefix code. Okay, now you will see some of the statistics regarding or the properties of these prefix codes. These code word lengths of the code satisfy certain inequality. So this is the important condition here. These code words, what we represent as prefix, they should satisfy this Kraft-Macmillan inequality. What is that? So here K represents the symbols, different symbols. So this summation is for all the symbols. Summation of 2 power minus Lk. What's the meaning here? Lk is nothing but the length of the code word. For example, A is represented as a 0, 0, then Lk is 2 because we have 2 bits in a code word. How many bits in a code word? That is Lk, length of the code word. So 2 power minus Lk when you consider for every symbol. So this total summation must be less than or equal to 1. So this is the Kraft-Macmillan inequality. So this condition should be satisfied for the prefix code. And when you see this relation here, whether it represents something else, can you remember that? Or do you have any intuition here? For example, total summation of something is less than or equal to 1. So is it similar to the probability? We will see that. So we know that summation of probabilities, when you consider different symbols, that must be less than or equal to 1, right? So that is nothing but this symbol, I mean 2 power minus lk, is also can be represented as pk. That is a probability of every symbol. So 2 power minus lk, the term here, is also can be seen as the probability of every symbol, because if you replace this by pk here, what do we get? The summation of probabilities is less than or equal to 1. That's also true. This is also true. So we can just have a mapping between 2 power minus lk and pk, direct mapping. So then the prefix code with this code word lengths can be constructed. Please remember that all prefix codes are uniquely decodable. This is what we have discussed. If it's a prefix code, then it must be uniquely decodable at the receiver. There should be no confusion. But the converse is not true. If it is uniquely decodable, it does not mean that it is a prefix code. Okay, the prefix codes distinguish from other codes. Why? Because the end of the code word is always recognizable. For example, we have constructed a tree for a given prefix code. So you know when you need to stop. When you arrive at the leaf node, that's the end of the symbol, right? That's the end of the bit patterns in the code word. So you can recognize what symbol it is. So that's a important property here of prefix coding. And then the prefix code is also called as instantaneous code. Why? Because when you start uh, reading every bit in a code word, and if the binary sequence is fully received, then you know what's the particular symbol is. For example, when you start reading a sequence of bits, for example 111, okay, you know that's the end of this particular symbol E. You can immediately decode it. So that's why it's called as instantaneous code, because once you read all the binary sequences, you know what the symbol is. So now we have an important relation here. So this is the average length of the code word, and h is nothing but the entropy. So entropy value is less than or equal to the average code word length, but its average code word length is less than entropy plus 1. So this is an important relationship. Always it will follow this property. So from the previous discussions, we have seen that summation of 2 power minus lk is less than or equal to 1. And we then replace 2 power minus lk by probability. That's what we have written here. So the average code word length is represented as summation of lk divided by 2 power lk. So because in general, for example, in case of Shannon encoding or previous algorithms, we have seen that the average code word length is nothing but lk multiplied by pk, right? So here lk multiplied by pk. What is pk? Pk is nothing but 2 power minus lk, or lk divided by 2 power lk. So this is the general equation. Lk multiply pk is the general equation for average code word length. We are just replacing here. Lk is as it is. Instead of pk, we have used this term here. Okay, then how to represent entropy? Entropy is nothing but, in general, pk log by 1 by pk, right? So here we have pk. The pk is represented by this term, pk log of 1 by pk here. So that's the equation for entropy. That's what represented here. So simplification leads us to this point, because we are just simplifying this term. Okay, finally, from the previous point, that is L average length is greater than or equal to entropy, but less than entropy plus 1. So here we have some n. So that represents the nth order. nth order, maybe second order, then we know how to represent entropy second order. That is 2 times the entropy of first order. So H of n is nothing but, or it's equal to n times H, right? For example, second order entropy H of x square is nothing but 2 times H of x. Similarly here, the n represents the order. So this is the general condition. So these are some of the statistics or the properties of prefix coding. So this is the end of today's lecture.